students. So, but first of all, I would like to announce that this is, we have today the first anniversary in our series of quantum seminars. This is the 10th seminar in our series. So, welcome everyone, and glad to see everyone. So, and it's my pleasure to introduce our today's guest and speaker, Professor Jan Kuneš from the University of Brno. Let me start with his career. So, as he said, the good Czech students graduate as good Czech students. He graduated from Charles University in Prague in 1997. And he already chosen the very interesting field of research and devoted his thesis to vortices in transition metal oxides, and then he focused on magnetism is in condensate matter theory and solid state compounds. So he obtained his PhD in 2002 under supervision of Professor Pavel Novak. And after that, he moved overseas to University of California, and where he was a postdoc in the group of Professor Warren Piquet. He spent about 3 years in California, and after that obtained von Humboldt Fellowship and joined the group of Dieter Wohlhardt in the University of Augsburg, Germany. There he worked as a research fellow till 2009 in the group of Professor Dieter Wohlhardt, an expert in and one of the initiators of dynamical means field theory. After that, he came back to Prague, to the Institute of Physics, Czech Academy of Sciences, and worked there as a senior researcher. Obtained several grants for projects on the international scale, and the most outstanding, I would say, he obtained ERC Consolidator grant. So in 2015, where I had occasion then to join this project on excitonic magnetism in Prague. And one good thing, maybe a good example about European Union research projects. So it's a kind of outstanding event for me, was that the professor who obtained ERC grant can move with the money and with the team to another university, even to another country. So we went together and Professor Kuneš obtained associate professor in University of Technology in Vienna, TU Wien, Institute of Solid State Physics. And so we moved smoothly from Prague to Vienna together and continued working smoothly on the project. So it was a great time working together for me, especially under this project. So since 2016, he was working in this Institute of Solid State Physics at TU Wien, and currently he is in Vienna as well. But so he is also employed at Masaryk University, Brno, Czechia, and smoothly transforming them back to Czechia. So as a curious fact about our today's speaker, maybe this is the first time we have a person who actually was acting in a movie that received Oscar and also Golden Globe. So the movie was 1996, Kola, Maybe some of attendants know this movie. If not, then I would strongly recommend to watch it in your free time. And maybe you will notice, maybe with some hints, also our today's speaker. I could notice only with some additional hints. Yeah. So please maybe memorize the movie call about actually human values. They are very important nowadays about humanity, about empathy, and it's a very positive actually and motivating movie, I would say. And talking about humanity, I would say that our today's speaker is strong supporter of Ukraine and our war for sovereignty, independence today, and he strongly supports Ukraine with aid as well, and always suggested us some additional help if he also asked every time how he could help us. So that we deeply appreciate that. And so using this occasion, I invited him to give a talk, and I think this is the best what he could do at this moment for us by providing a talk on the topic he has the best expertise. So today's talk is devoted to excitonic way to alter magnetism, and we are very much looking forward to the talk. Please, Professor Kuneš, the floor is yours.
So, Andrei, thank you very much for this very nice introduction. I have to say at the beginning that I'm really impressed by this seminar and how it runs. And I have to say, when I saw the list of your speakers, I was really humbled. So I hope you will enjoy my today's talk. So I will start sharing. So I'm going to talk about my favorite topic, which is condensation of spinful excitons. And I will try to put it to a modern context of altermagnetism, which is a research topic which appeared a few years ago and which we had an opportunity to contribute a little bit to as well. But before I start, let me acknowledge the people that actually contributed to the results I'm going to show you today. All of them are my former postdocs. Dominique Geoffroy, he's now in France back in banking. Atsushi Hariki, who's now a professor at the Osaka Metropolitan University, and Andrei, our today's host. So what is the altermagnetism about? Well, if you think about collinear magnets in non-relativistic systems, so without spin-orbit coupling, we have a magnetic systems where all the ordered moments are aligned in one direction. So you can have basically two possibilities. Either the magnetic sublattices which are connected by symmetry are aligned with each other, and this includes ferromagnetism and also ferrimagnetism, or they are anti-aligned, and then we get an anti-ferromagnet with zero net magnetization. So this is a real space classification. Now, as solid-state physicists, we are used to work with infinite systems, with periodic lattices, and so we are used to look at things also in reciprocal space. So if you look at this magnetization in reciprocal space, we can call a ferromagnet an S-wave system. S-wave because it's the only spherical harmonics which actually give us some finite net contribution. Well, antiferromagnet in this classification can be either no wave, so we have no magnetization anywhere at any K point, but we can also have other spin textures. We can have P wave, we can have D wave, which is represented by this now much studied material, ruthenium dioxide. We can have higher order spherical harmonics like F wave in manganese telluride. And so this K-space classification led to a new term, altermagnet. So basically altermagnets are collinear magnets which have this finite spin textures in reciprocal space, but they do not belong to this no wave class, which is now reserved for, so to say, classical antiferromagnets. And the basic feature, the reason why we can have these spin textures is that there are additional symmetries. So the symmetry that connects these magnetic sublattices is not only translation or inversion symmetry, but there is typically some kind of rotation. So this would be an example of ruthenium dioxide, where the two sublattices are related by 90 degrees rotation of the underlying orbital or crystal environment. So this topic appeared about 4 years ago, and it had really started generating many high-profile papers, even this editorial in PRX. So the question is, what is so interesting about these altermagnets? Well, they are characterized by spin-polarized bands. So this is an example of ruthenium dioxide. This is cut through the Brillouin zone. This is a picture of the Fermi surfaces, and you see that the Fermi surface for spin up is different from the Fermi surface for spin down. They are actually rotated with respect to each other by 90 degrees. So this may appear to be just a curiosity, but it has also important technological consequences. These systems actually exhibit properties that were previously associated mostly with ferromagnets, such as anomalous Hall effect, linear magneto-optical effects, such as circular dichroism, and other effects in transport, which can be used in practical applications. So what I'm going to do today is actually show you a different way to these spin textures. And I'm going to show you that we can obtain these spin textures, collinear spin textures, obtained by spontaneous symmetry breaking, even without any magnetization or any magnetic moments in the direct space. And I will use a very simple two-orbital Hubbard model to actually get these phases. So this takes me to the second topic of my talk today, which is excitonic condensation. And one way to approach this topic is to look at atoms with partially filled shells, let's say partially filled D shells, and we look at a special type of atoms. We look at atoms where the ground state is actually a singlet. And examples of these are plentiful. For example, if we have a cubic or octahedral crystal field and we put cobalt 3+ or iron 2+ in this environment, or if we include a cubic crystal field plus strong spin orbit coupling and take iridium 5+ or osmium 4+ or ruthenium 4+, they all will exhibit a singlet ground state. So the question is now, what's going to happen if we build a lattice out of these atoms? And at first, this looks like a stupid question, because it's something like combing a bald head, right? We don't have any kind of degrees of freedom to order here. However, if the first excited state, or if the excited states are not far away, an interaction between the excited states on neighboring atoms, or between the ground state and the excited state, can lead to a new physics. And there is kind of a literature or interest in this kind of physics, and there are a number of papers that appeared in recent past. There are also experimental realizations, not many, I have to say, but we have, for example, this praseodymium doped cobaltates, where the splitting between the ground state and the excited state is due to a crystal field, or calcium ruthenate, where this splitting is due to spin orbit coupling. Or we can even have these magnetic systems. So these are like Heisenberg model dimers, where this singlet triplet physics actually take place on a dimer of spin 1/2 systems. And these all are studied also experimentally. Well, there is much older way to this excitonic condensation, which comes from the weak coupling side and which goes back to Sir Neville Mott in early 60s. And what Mott observed was that if you take a bent insulator and start by some external means, for example, pressure, closing the gap. If there is an electron-electron interaction, as it is in any material, it cannot happen that these bands are simply start crossing each other. When the attractive energy between the electron and the hole overcomes the band gap, which is the energy necessary to create the pair, we actually get an unstable situation, and there will be a phase transition to a new state. And this will be the excitonic insulator. The excitonic insulator in the weak coupling limit is actually something that's very similar, at least on a mathematical level, to BCS superconductor. And it was also studied in this context much in the 60s by some of the prominent physicists. And it is still, there are still works in this direction in the recent past. Well, the experimental realizations of excitonic insulators and excitonic condensates are, let's say, more controversial. There are materials which are discussed in this context, but I would say the only very clear experimental proof of this excitonic condensation comes from this work of Eisenstein and McDonald, who studied actually a bilayer of quantum wells. So basically we have two layers where the electrons can move only in two dimensions, and they are separated such that the tunneling amplitude is essentially zero, but the electrons can still interact with each other. And they showed by tuning the perpendicular crystal field, which effectively changes the population of electrons and holes in the available states, that when the number of electrons and holes are approximately equal, there is a transition to this excitonic condensate state. So the charge carriers in the different layers do not respond to an electric and magnetic field independently, but they respond like one neutral entity. And they also could prove by measuring the tunneling rate between the two layers that this is indeed a coherent state. So now let me go to my model, and let me talk about this this two orbital Hubbard model, and let me start building this model from the two orbital atoms. So let's assume that we have these two orbitals. You can think about some perovskite structure with x squared minus y squared and xy orbitals. Important thing here is that there is a crystal field splitting delta between them, and then we include standard electron-electron interaction in Slater-Kanamori parametrization. So we have the charge-charge part, we have the Hund's exchange, and then we have the part which depends on the orbital shapes. Now we build a crystal, a two-dimensional square lattice of these atoms, and we will consider the hopping between nearest neighbors. We will consider hopping which goes primarily between orbitals of the same type. And this would be indeed the case if we take these symmetries of orbitals. Only these hoppings will be allowed by symmetry, but later we will also consider a cross hopping, so hopping from A to B and B to A on neighboring sides. And if you want to have some idea of how it could be realized, you can think about tilts of, let's say, transition metal oxygen octaedra in such a structure. So this is our model. We don't consider any non-local interactions. So this is a model of Hubbard type, and we will be looking at half filling. And again, if you prefer formulas, here we have the crystal field splitting. Here we have the hopping between the same type of orbitals, A to A, B to B. Here we have the cross hopping, and the remaining parts is the local interaction, which is part of it is diagonal in the orbital number, in the occupation number basis, and then we have spin flip and pair creation, which are not diagonal. So let me now say a few words about what we can do analytically about this model. And a very instructive limit to study here is the strong coupling limit, where the hopping between atoms is actually treated as a small perturbation. And we will choose a special special range of parameters. So if we think about all the 2 electron local states possible, we will have this singlet, then we will have this singlet, then we have the triplet, so this would be the so-called high spin state, and then we have this singlet where the 2 electrons occupy the lower lying orbital. And now if we choose the parameter range where delta is approximately equal to 3J, you see that these 2 states are almost degenerate, and these 2 states have higher energies. So we will take them out of our picture, and we will build a model only on the space spanned by the low spin state and the high spin state. So this model can be kind of translated in a bosonic language in which the ground state, which is the lattice field of low spin state, will be our bosonic vacuum state, and the excitations, which are the high spin state, and they come in 3 flavors, as I explained before, will be a bosonic excitations which carry a spin 1. And now we can look at the possible processes. So here's an example of one of them. Let us look at this pair of neighboring sides, and we start with the low spin state on the left and the high spin state on the right. And now we can have this hopping process to an intermediate state, which has energy which is larger by the order of U, which is followed by the hopping of this electron in the opposite direction. And the result of this process is that our excitation, our exciton moved from the right side to the left side. And the amplitude for such a hopping process is Ta times Tb over U. So this is the first important observation, that the excitons are actually mobile. Now we can, of course, go through the bookkeeping of all these possible second order processes. So we have this exciton hopping, which is this process. We have all sorts of diagonal hoppings, which lead to exciton-exciton repulsion, and also exciton-exciton exchange interaction. And if we have this cross-hopping, we can also have pair creation and pair annihilation processes. So if we just summarize all of these, we get an effective Hamiltonian for the excitons, which have some excitonic creation energy. Then we have an amplitude for the propagation of the excitons. Then we have a repulsion between excitons on the neighboring sides. And then we have the exchange interaction between the excitons. And in this picture, this D vector describes this triplet. So it can be either labeled by the SZ, so SZ equal to 0, -1, and +1, or we can use this Cartesian representation where we call them dx, dy, and dz, and there is this simple unitary transformation between the 2 pictures. So now this Hamiltonian is easy to solve in the mean field approximation. This is how the phase diagram looks like. I want to show you only the basic features. So if we look at this phase diagram as a function of this excitonic creation energy, on the far right, the ground state is just the vacuum state. It means we have a low spin state everywhere. It's kind of a trivial state. If we are on the far left, where this epsilon is negative, we will have high spins everywhere. And so the only non-trivial term which remains will be this one, and we will get the Heisenberg model of spin 1 with spin 1. Well, the interesting things happen in between, where the low spin and high spin states are actually competing, and we can get phases like a solid of these excitons. So this is a high spin, low spin, high spin, low spin checkerboard order. But the really interesting state that we are going to talk about is this one. And so if we start on this side and we think about the elementary excitations above the vacuum, well, we have these excitons, and because they can hop, they have a dispersion. So this is a dispersion of such an exciton on a square lattice. And now if we start reducing this this exciton creation energy, well, we will start closing the gap. But what's going to happen? Well, when the gap is closed, of course, the energy of the excitons cannot go negative because they are bosons. So there is a phase transition, which is a Bose-Einstein condensation of these excitons. And this is reflected in the excitation spectrum. So we get this linear mode. And because we have this additional structure, because the excitons are carrying this spin degree of freedom, there is also another mode which will have a gap. Now, let us look at what the excitonic condensate actually is. And let me start by saying what it is not. So if we look at this point, if we are in the normal phase at an elevated temperature, the state that we will have will be characterized by finite population of the excitons. At least in the low density limit, it will be simply the Bose-Einstein function associated with this excitation energy, but there will be no coherence. So the expectation value of the excitonic or of the bosonic operators will be 0. So the state will be a statistical mixture of vacuum states and these bosonic states. On the other hand, when we go into the ordered phase, and we are now at low or 0 temperature, we get this excitonic condensate. And the wave function of this condensate can be, in a good approximation, written as a product wave function, where we have this state Ci on every side. So this is repeated, and the state Ci is simply a linear combination of the vacuum state and of the bosonic state. So again, we have a finite population of the excitons, but now the expectation value of the bosonic operators is non-zeros. So you can see, well, because we have both in the linear combination, we will get combinations of type A times B. So this is an order parameter for Bose-Einstein condensate. But there is one very interesting feature, which is related to the fact that our excitons have this additional internal degree of freedom. Namely, we can form a distinct type of condensates. So you can imagine that we form a superposition of the vacuum state with a state that is fully polarized in some direction. So in this case, I picked up minus z-axis, so sz minus 1. So obviously, this state will also have a finite net magnetic moment. So this will be a ferromagnetic condensate. S is non-zero. Now, you can think about this type of condensate with the state sz equal to 0. Well, this state has no magnetic moment. The expectation value of the magnetic moment in any direction of this state is 0. So the net magnetic moment in this state is 0. So obviously it cannot be symmetry related to the ferromagnetic condensate. So this is so-called polar condensate. Well, the term which distinguishes these two states is this exchange term. So if we, So if this exchange term is negative, so if there is a ferromagnetic exchange, we get a ferromagnetic condensate. If this term is anti-ferromagnetic, so positive, we get this polar condensate. And this is another example of a polar condensate wave function, which is the one we are actually going to see later in the calculations. So yeah, so this is the strong coupling picture, which is a useful reference. But now we want to go back to fermions. So we want to go back to our 2-orbital Hubbard model, and the calculations here cannot be done on a piece of paper. So we need to use quite heavy numerics, and the tool we are going to use is dynamical mean field theory. And the first question is, what is the order parameter that we are looking for in the fermionic language? And we can kind of use the analogy to the bosonic language. So in the bosonic language, the order parameter was the expectation value of this creation and annihilation operator, which took low spin into high spin and vice versa. So analogically, in the fermionic case, the operator that takes this one into this one is annihilation of spin down electron in b orbital, followed by creation of a spin up electron in the a orbital. So it will be an expectation value of the type a dagger b, but now we want to flip the spin, so it would be a up, b down. In general, we can arrange these expectation value into the spin triplet combinations, so they can be labeled here by these Pauli matrices. I will get to the structure of this order parameter a bit later when it becomes important. Now, the tool we are going to use, and I'm going to say only a few words, is the dynamical mean field theory. You can view it as an analogy of the Weiss molecular field theory that you might know for spin models applied to fermions. So the conceptual picture is the same. We replace the difficult lattice model by an effective local model where we treat the atomic physics exactly, but we couple the atom to the rest of the crystal by means of some effective bath, which is determined self-consistently. The difference between the Weiss molecular field theory and dynamical mean field theory is in its complexity. In the Weiss molecular field, basically the molecular field is number. In dynamical mean field theory, the molecular field is actually a function. It's frequency dependent or time dependent, depending on which kind of representation one uses. So that's it about the technique. And now I would like to show you some numerical results. So from now on, we restrict ourselves to the part of this phase diagram where only the excitonic condensation is relevant. So I'll be looking at this part of the phase diagram. And first, let me show you that we indeed, in the numerics, can get this excitonic condensate and that it has the properties that we could anticipate, let's say, based on the strong coupling model. So these are the parameters where we did the calculation for sake of completeness. And what I'm going to show you now is the evolution of various physical quantities as we go across the excitonic condensation transition from high temperature to low temperature. So first, this is the order parameter. And yeah, indeed, at high temperatures, we get 0. And at low temperatures, it follows the square root typical behavior for the mean field theory. Importantly, here, the excitonic condensate, which we get is the polar one, which agrees with the fact that in the Hubbard model, the effective interaction between the neighboring high spins is antiferromagnetic one. So that leads to the polar condensate. Now, what we don't have in the strong coupling model is actually the fermionic characteristics. So what I show here are the spectral densities that are obtained at the different temperatures. So let me show you also the band structures. So this band structure is in the normal phase. We have the lower band, the valence band, which is formed mostly by the b orbitals. This is the corresponding integrated spectral function or density of states, if you want. And this is the upper band, which in our model is broader and which is formed by the a orbitals, and they overlap slightly in this regime. And now, as we progress, as we decrease the temperature and the spontaneous hybridization, which is characterized by this order parameter, develops between the two bands, a gap opens. So this is the band structure which corresponds to this temperature, and you see a well well-developed gap. And those of you that are familiar with the BCS theory, you know that this is the same picture as that you see in a BCS superconductor. So in a BCS superconductor, these peaks would be the so-called Hebel-Schlichter peaks. And you see that in this region, these functions are actually hybrids or superpositions of A and B orbitals. So for example, if you look at this peak, you have a lot of A weight as well as B weight. Now, you can ask, well, where are the excitons here? Well, here there are no excitons. So this is a one particle picture. So we have we are asking the question, what happens when we add an electron or when we add a hole? To see the excitons, we have to ask a question, what happens when we add an electron-hole pair? So we have to go to two-particle response. So this is actually numerically quite a bit more demanding than these one-particle calculations, but can be done for the simple model as two-orbital Hubbard model. And so what I show you here are these correlation functions. I'm not going to explain these in detail. I'm just going to say that this is indeed an operator which creates certain exciton, which is later annihilated. And then we look at the Fourier transform, and we looked at it in a k-resolved way. So what you see by looking at this correlation function is essentially the dispersion of the exciton that we have seen in the strong coupling picture. And now these different rows correspond to changing this crystal field splitting. So basically, we are now closing the gap in the normal phase. So this is normal phase, and now we are closing the gap. And now we go to the ordered phase. And what you see here in this heavy numerics is analogy of this strong coupling calculation, where we have one linear mode and one mode which closes the gap and then reopens as we move away from the transition deeper into the excitonic phase. Okay, so this takes me to the end of my introduction. So basically what I tried to show you so far is that in this two-orbital Hubbard model, we indeed have this excitonic condensate phase, and that it has the properties that we expect from an excitonic condensate, both on the one-particle level and on the two-particle level. Now, to move on and to finally get to the spin texture, which I promised at the beginning, we have to add additional degrees of freedom. And the first degree of freedom we are going to add is doping. So far, in this phase diagram, we were moving along this line. So we were at half filling, and we were changing the temperature. Now, when we add the doping, we are essentially probing similar physics like what I showed you in this Eisenstein-McDonnell experiment. So we are going to move away from the perfect balance between the number of holes and number of electrons. And indeed, as in the experiment, we see that the excitonic condensation is suppressed, and it disappears at, well, relatively moderate doping. But before that actually happens, something interesting happens. We go from this polar excitonic phase to the ferromagnetic excitonic phase. And now to understand how we can identify these phases, we have to look more closely at the structure of the autoparameter. So as I mentioned before, the autoparameter is a vector indexed by the direction in spin space. So it's a three-dimensional vector which carries the vector character of this Pauli matrix. But in addition to that, well, this operator is non-Hermitian. So it actually represents two possible Hermitian operators, the real part, which would be A dagger B plus B dagger A, and the imaginary part, which is A dagger B minus B dagger A times imaginary unity. And so, in fact, this autoparameter has 6 components. 3 represent this direction in the spin space, and 2 represent the direction in this, let's say, phase space. So the real and imaginary part of this vector. And these should be treated as independent vectors. So now if we go back to this phase diagram, well, one can show that in the polar condensate, the order parameter must have a character of a real vector times a phase, which in terms of these 2 components means that the real component and the imaginary component are parallel to each other. This phase with no cross-hopping can be arbitrary, so there is still a lot of degeneracy in the space of possible phases. Now, if you look at this ferromagnetic phase, well, this ferromagnetic phase is characterized by the fact that the real component and the imaginary component are not parallel. Actually, it turns out that they always come to be perpendicular to each other. And this perpendicular orientation of the real and imaginary component gives rise to a magnetic moment, which is perpendicular to both of them. So I will explain where this comes from in a moment, but first let me point out that these are indeed distinct phases because they obviously have a distinct symmetry. So this one breaks the full SU2 rotation symmetry in the spin space, but there is still a uniaxial symmetry, right? I can still rotate around the common direction of these 2 vectors, and I will not change my system. Whereas in the ferromagnetic EC phase, well, I cannot rotate anything without changing the direction of these vectors. So there is no residual symmetry in the spin space in the ferromagnetic EC phase. Well, you can also see that it is distinct from normal ferromagnet, because in normal ferromagnet, I would have only this vector, and so I would have a uniaxial symmetry between around the direction of this vector. This is not the case in this ferromagnetic excitonic condensate. So where does this come from? Well, it's again quite easy to see when we go to the strong coupling limit, and we can ask, what is this S operator actually in terms of our bosonic operators? It's quite simple. SZ is simply the number of excitons with SZ equal to 1 minus the number of exciton with SZ equal to -1. And now if I go from this basis, from the 1 - 1 0 basis to the Cartesian basis, and you have to believe me that I did the algebra right, you get a dx dagger dy minus dy dagger dx. And you can do it for all Cartesian components, and you find indeed that the S operator is I times d dagger cross d. So if we are now in the condensate phase, we can replace the operators with the expectation value, and we get this relationship. Actually, I should not write here is equal. It's proportional to. There is some constant in between. So this explains the relationship between the existence of this perpendicular magnetic moment and the orientation of the real and imaginary part of the order parameter. I want to make here one more point, namely that this term, which distinguishes these 2 phases, is quartic in the Ds, while the term which is actually responsible for the phase transition is quadratic, which means, well, when we are close to the phase transition, the quadratic terms will always take precedence over the quartic terms. And that will turn to be important right away when we include the cross-hopping. So including cross-hopping, and we will consider 2 types of cross-hopping. We will consider cross-hopping, which is even, so hopping in this direction and this direction has the same sign. If you want to think about it in terms of orbitals, you can think about s orbitals everywhere. So if I have s orbitals everywhere, this overlap and this overlap will have the same sign. Odd cross-hopping would, on the other hand, correspond to orbitals which have opposite parity. So if I have s orbital here and p orbital here and here, I would get this pattern of cross-hoppings. And in the strong coupling picture, it's clear that this cross-hopping leads to a creation of a pair of excitons out of vacuum, right? So I can create excitons in pair, or I can annihilate excitons in pair. And so after a little bit of algebra, these type of processes in the strong coupling limit add this term into my Hamiltonian. And now this term is quadratic in these, so at least close to the phase transition, it will play a more important role than this exchange term. The other thing to observe is that the terms that we have used so far were insensitive to the phase of the order parameter. You see, there was always a combination d dagger d, and these also had d dagger d in there. So the phase didn't play any role. Why these do? These are sensitive to the phase, and therefore, depending on the sign of these of this constant k1, we either get an order parameter which is purely real, or we get an order parameter which is purely imaginary. And the choice is simply determined by the fact that we always want to get energy gain here. So we want to get a combination of these such that the whole expression here is negative, so it leads to energy gain. And that's why, depending on the sign of k1, we get either a real order parameter or purely imaginary order parameter. Now we can ask, what does it mean for in the real space? So the real order parameter leads to it doesn't lead to a magnetic moment, but it leads to a magnetic multipole. So we get a spin density, non-zero spin density on every side, which, however, integrates to zero. The specific distribution of spin depends on the underlying orbitals of our model, but there will always be some modulated distribution of spin density locally. Imaginary order parameter, on the other hand, does not lead to any spin density. So there will be a spin density everywhere in space will be zero point-wise, but we get something like a spin currents that are flowing between the two orbitals. Okay, so this is what we might expect by just looking at this Hamiltonian. So let us look at the actual calculations, and these are the main results that I want to show you. So this is first a calculation for even cross-hopping. So I will show you here in this table. So this is a perpendicular magnetization. So magnetization perpendicular to the order parameter. This is magnetization parallel to the order parameter. So magnetic moment, non-zero magnetic moment. This is a magnetization that exists in space. So this will exist if we have these non-zero magnetic multipoles. And this is the magnetic texture. So this is an expectation value of magnetization in k-space. So it's defined by this combination of orbitals. So what we find here, that in the for the even cross-hopping, at low doping, we have a purely imaginary order parameter, and we get an order which has no magnetic moment, no magnetization, point-wise in the continuum space, and no M of k. So this is, but we still break the symmetry. There will still be a special direction in the spin space. So this is something that one would call a nematic phase, where we have no ordered moments, but we break the spin rotational symmetry. Now, if we dope the system at high doping, we switch from the imaginary order parameter to a real one, and here we always get magnetic multipole. We always get some texture in the spin space, and depending on the specifics of the model, we either get a magnetic moment or net magnetization, which is parallel to the other parameter, but we can also get a zero magnetic moment. Now, if we go to odd cross-hopping, the situation is reversed. This is because we changed the sign of our coupling constant in the model I showed you before. So at low doping, we get these magnetic multipoles, but we get no spin texture. But if we dope to high doping, we actually get a state where we have no magnetic moments, no spin density anywhere in the space, but we get a non-zero spin texture. So this is quite interesting state. So let's look at it in a more detail. So this is a plot of the spin texture, actual calculation, numerical results. So this is let's say spin up dominant, and this is spin down dominant region in the K space. Now we can ask various questions. So for example, one question would be, what happens when we apply an external magnetic field? There are a few possibilities, right? We need to develop some moment along the magnetic field, but we can, in principle, what can happen is that one of these regions expands and the other region shrinks. So if you want to think about it in antiferromagnet analogy, it would be like taking an antiferromagnet, applying a field, and one moment expanding and the other moment shrinking. Well, the other possibility, what actually isotropic antiferromagnet would do is that the moments turn perpendicular to the magnetic field and tilt a little bit in the direction of the applied field. And this is actually what we find happens in all the calculations we did for such systems, namely that the autoparameter turns perpendicular to the applied field. It develops a small real part, and that means there is a magnetic moment, net magnetization, that is now pointing in the field direction. Well, we can also look at the polarization in a K-resolved manner at band structure. So this is how the band structure of our model look like. This is how the Fermi surface look like, and this is now how the spin polarized band structure look like. So what you actually see here is a tiny. So you don't see spin polarized bands, right? Like what I showed you at the beginning in the introduction. And the reason is that here the spin splitting of the bands is really tiny. So basically you have like two peaks which are shifted a little bit. And now if you draw the difference, well, you will see this tail is more, let's say, spin up, and the other tail is more spin down. So that's precisely what you see here, that this is the position of the bands, and on one side it's more polarized in one direction, on the other slope it's more polarized in the other direction. The best you can see probably the spin splitting here. So the red is shifted a little bit to one direction, and the blue is shifted in the other direction. The interesting thing is that these textures, which are actually rather tiny, they survive to very high temperatures. So we are now talking temperatures about 200, even 300 Kelvin. And the parameters we used for the model are actually realistic parameters for transition metals or transition metal oxides when it comes to the bandwidth and when it comes to the interaction strengths. So in the rest of my talk, well, let me ask a question: where does this physics actually comes from? So where do these textures come from? And to answer this, we can again go to the strong coupling model, and we can ask a question: if we dope a particle in the excitonic condensate, how does it propagate? How can such a doped particle propagate through the excitonic condensate? So to answer this question, we have to calculate matrix elements of this type. So we take this dimer, and we start with a state where we have condensate on the right and a doped particle with some spin on the left. And we want to end up in a state where we have condensate left behind and the particle moves to the right. So this is the matrix element we want to calculate. And if we do this algebra, what we actually get is that there is indeed a hopping, which is just like the original hopping. It's spin independent. So it's modified. So the doped particles kind of do not move through the condensate as easily as they move through an empty lattice, but nothing happens to their spin. But there are additional terms there, and these terms depend on spin. So these terms are actually like bond exchange field. So this is a spin-dependent hopping, and this spin-dependent hopping is polarized along the external magnetic field. So this is along the perpendicular moment in the ferromagnetic condensate, but there is also a field which appears in the polar condensate when we have a cross-hopping. And now the reason why we have sometimes the textures and sometimes not lies in the interplay between the signs of these hopping parameters and the phase of the order parameter. So, for example, if we look back at the even cross-hopping, so V1 is equal to V2, we find that the order parameter wants to be imaginary. And that means that this term disappears. Only when we dope a substantial amount of doped particles, we actually flip the sign of, flip the phase of this order parameter, and we get a finite contribution. And then we can get when we go to the Fourier transform, we can get these spin textures. So I don't want to go through this through this detailed derivation where this comes from. I want to explain in the last few minutes. I want to explain the general principle, the general picture, because it's actually very similar to the double exchange mechanism that you might know from manganites. Basically, we have a system that favors some order, right? In manganites, for example, the large moments they form antiferromagnetic order. Here, the condensate wants to form some kind of order. For example, this as a spin density wave order. Now we add particles, and the condensate acts as a filter for these particles. So it restricts their motion. If I dope a lot of these doped particles, it actually makes sense to kind of open this filter to allow these particles to move more freely, to gain some kinetic energy, while sacrificing some energy in the condensate itself. So again, if I make the analogy to manganites, what happens if you dope a lot of free particles in the manganites? Well, the moments order ferromagnetically, because when they are ordered ferromagnetically, the doped particles can move freely, while if they are aligned antiferromagnetically, in principle, in the limit of large exchange, the filter is completely moved and the particles cannot move at all. So there is a compromise between the physics of the condensate itself and the physics or kinetic energy of the doped particles. The principle here is the same. Of course, the details, the way how this filter works, is a bit more complicated. Okay, so last slide before concluding. So what can we do with this? Well, we can play with the patterns of this cross-hopping. So I showed you that if we have this even cross-hopping, and it has the same sign on in both, let's say, the X and Y direction, well, as a result, we will get this S wave like spin texture. And this is a result of actual numerical calculation. Well, if we choose the cross-hopping pattern where we still have this even cross-hopping, so we have plus, 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 minus, 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 but it has opposite sign in the X and Y direction, well, we get this D wave spin texture. If we have the odd cross-hopping, so we get plus minus, where you see there is a symmetry along this diagonal, the effective bond exchange field will in this case be purely imaginary, and we get a P wave spin texture, which exists in K space, but in real space there is no magnetization anywhere. Okay, so this takes me to my final slide, and I will try to summarize. So I hope I didn't overwhelm you with too many kind of technical information. Well, what I tried to show you that this excitonic magnetism provides a really rich field, rich playground with potentially interesting applications. And now in the context of altermagnets, it's maybe a way to reassess or reapproach, because we understand that these spin textures can be quite useful also in practical applications. Well, the real excitonic magnets, the materials, are yet to be found. So far it's kind of a theorist playground. Perhaps one could think about realization in cold atoms and optical traps, where one could really engineer all sorts of models. While real material realization is still to be found. And finally, what I wanted to show you that we can indeed realize and in fact engineer quite sophisticated and quite complicated spin textures and spin polarizations, which are actually quite small but survive to rather high temperatures, which is what one actually wants in technological applications. So I would like to stop here and thank you for your attention. And yeah, I'm happy to take questions.
Thank you, Professor Kuneš, for a wonderful talk and interesting ideas shared with us. We are open for questions. Perhaps so I see one microphone unmuted. Is there a question or not yet? Okay, so you mentioned about candidates. So apologize. So what are the candidates with relatively high temperatures currently from the side of transition metal oxides or other systems?
Okay, so let me, I have, maybe I start with this one. So there is a whole series of this cobaltates. So it's praseodymium calcium cobaltate, which is doped in yttrium, so at different doping levels. There is a phase transition, which leads to what I would call at the moment a hidden order. So there is no consensus what is actually going on there, but there are indications that this state may be a realization of this excitonic condensate, and the transition temperatures, as you can see, are not. Maybe I can make it a bit bigger. Are not small, so they are around 100 K or close to 100 K, so nitrogen temperatures. Well, the other possible candidates or systems that people are studying is this calcium ruthenate, which I mentioned before, which where this is a system actually where a spin orbit is important, because the gap that is opened between singlet J0 and then J1 half state. That must be J1 state, which is open due to the spin orbit. So we have 4 electrons in T2G shell, and with spin orbit you have a singlet ground state and a triplet excited state. So the small disadvantage of this system is that you cannot independently tune the hopping of excitons and the cross hopping, which is responsible for these textures. So in my simulation, I showed you that we have a large hopping between the orbitals of the same type and small cross hopping. So if you are in the cobaltates, the cross hopping would correspond to tilting of the octahedra in the perovskite structure, and this is something that one can achieve, relatively easily. For the strucenate, there is actually only one hopping, and the cross hopping is given by this interplay between spin orbit and the T2G hopping. So there is no parameter which you would be able to tune to make let's say the cross hopping small compared to the diagonal hopping. This other material I mentioned, this is essentially a realization of a spin model which has this singlet triplet physics. So for example, what you see here are results of inelastic neutron scattering experiments which show the closing of the gap and reopening at the condensation transition. But here the physics is a bit different. So here, for example, the doping would not work because it's an analogical model, but it's realized by different degrees of freedom. So I think the main candidate still remains the cobaltates. The problem with the cobaltates is that it's as you well know, is that we have actually that the excitons actually carry not only spin, but it carry also an orbital flavor. So it's more complicated, and there is a strong tendency to form B excitons, which can kill the condensation. So instead of having condensate, we will get B exciton crystal or B exciton kind of plasma or liquid, which will prohibit existence of this excitonic condensation.
Okay, thank you. If I may, I would like to also ask, maybe you talk to experimentalists from cold atoms about possible realizations. So as far as I know, the direct hopping is more or less easier. So to construct two-band Hubbard model with cold atoms in optical lattices is relatively simple, but I'm not familiar whether they can realize these cross-hopping terms, which seem to be kind of essential.
I don't really know details about this. So I cannot answer how hard it is to engineer this cross hopping. Well, in principle, to get the condensate, you don't need the cross hopping. So it's just the different knob which allows you to get these kind of more fancy features. So already getting the condensate would be quite interesting. Of course, it exists in a range of parameters, but still you have to be tuned. Where do I have it? So fairly close to this limit. I mean, it's not fine tuning, so you don't have to be tuned. They don't have to be equal to like 1%, but they can be, I would say, perhaps 10% off, and you still can see this physics.
Okay. Yes. So seems manageable then. Maybe not
Yes,
this
may I
rich physics. Yes, please.
So I have a couple of questions. The first one is, as far as I understand, you speak about Frankel excitons, right?
Yes.
Because from the very beginning you said about MOT, but here definitely Frankel excitons. And
That's
the second
right.
question is more complicated. Usually, you said about the possibility of this spin flop-like phase transition in the spin space for your system. However, for this spin flop transition, it is necessary to have the magnetic anisotropy, which is absent from the very beginning in your calculations. From the very beginning, you do not have this. You have only field, but the field does not help. The field itself, the magnetic field itself, does not change this phase transition. So it is not. It seems like not the case. What is the origin? And you mentioned that in this phase, as far as I understand, there is no spinematic ordering, so no anisotropy at all.
So okay, so let me answer first the spin flop question. So basically,
it is related.
So basically, your question is about. Wait a second. So how do I go from this phase to this phase, right? So how do I go from something that looks like easy axis to something that looks like easy plane? In fact, you don't
know. In fact, it is only possible to change the sign of the magnetic anisotropy.
No, actually, what distinguishes these two phases is what I can have is either SU2 full SU2 symmetry, or I can have easy axis. If I have easy axis and isotropy, I can have this transition with only a Z+1 and a Z -1. So in that case, I would go from this state to this state. So this is also polar condensate, and I don't need this S equals 0 state, which would be like the state favored by the easy plane anisotropy. I don't need that state at all. But in principle, if I have no anisotropy, well, this state, this polar state, and this state, they are degenerate. They are just rotation of one another. Actually, I should, to be completely precise, I should put here divided by square root of 2. But they are the same state, just related by change of spin coordinates.
By the unitary transformation.
Yeah. Well, rotation, right? You need, I mean, in principle, there is a, so that's the difference between I can go from this state to this state. Well, there is a unitary transformation, but it would be some SU3 rotation, and that's not a symmetry of my Hamiltonian. So I cannot, that's why this phase, this state and this state, they are not mapped to one another by SU2 rotation. I cannot go from one to another by rotating the spin. And that's why they are different. They have simply different energies if I evaluate the expectation value.
But for SU3 symmetry, you need some pneumatic the parameter, right?
That's so for
SU2.
So if you look at the this Hamiltonian, so this term obviously has an SU3 symmetry. This one also has an SU3 symmetry. I can make any unitary transformation in the space of the bosons. This state, this term has also SU3 symmetry. It's invariant under any rotation of the bosons, but this one does not. So if K is equal to 0, then this state and this state, they are equivalent. They can be rotated to one another by the symmetry of the Hamiltonian. That's also a reason why, if I look at the, well, do I have it here? I have both of them. So if I look at this point, well, this will be the point precisely where K0 is 0. So here it's effectively, here it's positive, I have antiferromagnetic interaction. Here it's negative. Here they touch, and I have effectively SU3 symmetry at this particular point of of my phase diagram or of my parameter space.
Okay, thank you very much.
Sure.
Andrei, your microphone is muted.
Yeah, thank you. Are there further questions to the speaker? Well, if this is not the case, I would like to thank Professor Kuneš and finish the official part of questions, because we have also informal question about my introduction from Yaroslav Bazali,